What's up guys, welcome back to the channel. In this particular video we are going to discuss a problem, partition equals subset sum. This problem is a standard DSA problem guys and asked by many companies, so make sure you stay tuned till the end of the video. Starting with the problem statement, so it's quite simple and straightforward. It says that you are given an array ARR of size n. You have to check if it can be partitioned into two parts such that the sum of elements in both the parts is same, right? Now an example is given here guys. Let me write the example here. So I have an array which contains element 1, 5, then 11, then 5. I have to partition this array into two parts such that sum of both the parts is same, right? So what I can do is I can choose this element, then this element, then this element. This is going to give me a set 1, 5, 5. The remaining set is containing a single element which is 11, right? Now guys, let me calculate the sum of elements in both the sets. So this set contains the sum as 1 plus 5 plus 5 which is equal to 11. After this set contains the sum 11 again. So guys, you can see that the sum of both the sets is equal, or both the partitions is equal. So I can partition this array into two parts, right? And these are the given two parts. Now guys, the output for this particular example is going to be yes, because we can partition, we are able to partition. Talking about one more example, so let's say I have an array which contains element 5, 7, 1. So guys, for this example you can see that I cannot divide like this particular array into two partitions so that the sum becomes equal, right? So for this the output is going to be no. Now guys, I hope you have understood the problem statement. So let's talk about the solution now. Okay, so guys, unlike any other day, I have written two examples today. And before we talk about the approach, I want you to observe something here, guys. See, what is the sum of elements in this particular array? So the sum is equal to 22, right? And what is the sum of elements in this particular array? So sum is equal to 11. So see, guys, let me start with this particular array first, which is the first example. So I want to divide this particular array into two partitions which contains equal sum. This is what the problem says, right? So guys, see, if I want to divide this particular array into two partition which contains equal sum, so isn't it very similar to dividing this particular sum into two equal parts? So each equal part will contain 11 sum, right? And even this is true, guys. You can see that if I divide this particular array into two partition which contains equal sum, so each part is definitely going to have the sum as 11, right? Because 22 is the sum of whole array and I want to divide this particular array into two equal sums. So what about this particular example? Here you can see that the sum is 11. So if I want to divide this particular array into two equal parts, so this is very similar to dividing this particular sum into two parts which are equal, right? So each part should contain 11 by 2 sum. But 11 by 2 is not going to give us an integer. It will give me 5.5 or something, right? So guys, you can see that one thing, uh, any subset cannot have a sum as 5.5. Why I am saying this? Because I have only integer values in the array and the sum contains one decimal point, right? So guys, this is not possible. I can write this observation. If the sum of array, like if sum of array is odd, right? So if sum mod 2 is equal to 1, then I can directly return false, isn't it guys? Isn't it? After this, the second thing is, if the sum is even, if the sum is even, guys, so in that particular case I will first divide the sum into two parts, right? And each part is going to have the value 11 in this particular case, right? So you can see that I'll simply take the half. I'll say that okay, half is equal to sum by 2, and now I will simply look for the subset which contains the sum equals to 11 in this particular array. If I am able to find a subset which contains sum equals to half or sum equals to 11 for this example, then the remaining subset is automatically going to have the equal sum, right? This is like I have an array which contains sum as 22 and I want to find a sub array, or my bad guys, I want to find a subset which contains the sum 11. So the remaining subset is automatically going to have sum 11, right? Because the sum of array is equal to 22. So I will simply do one thing. I will call a function, and this function is going to look for sum equals to half in a subset, right? So this is like subset sum problem. Let me write array here. So guys, see, in this particular array I want to find a sum whose value is equal to half. So I want to find like I want to find a subset, guys. So this is what the subset sum problem says. It says that you have to find a subset which contains the given sum, right? So now I just need to write the logic of subset sum problem and my task is done. Before that, we have to calculate the sum of array as well. We have not calculated, so it's quite simple. We can simply initialize sum equals to 0, then we can iterate over each value. I'll say that okay, for I equals to 0, then I is smaller than n, then I plus plus. After this, my sum will be plus equals to array of I. So this is going to give me the sum. Now guys, this is the main approach that we are going to follow. Now we are just left with this particular check function, right? So let me explain this check function in detail. Okay, so I have written the same example, guys, and you can now see that the target is equal to 11, right? I have already explained the reason behind this and the intuition behind this. Now check function is going to check if we have a subset with given sum, and this is what exactly the subset sum problem is, guys. The subset sum problem basically says that find a subset which contains the given sum, and that problem is again a very important standard DSA problem. So make sure you do that particular problem as well. I am going to explain how you are going to do that particular problem, right? So this particular is a part of the current problem that we are solving. And see, the first approach that will come to anyone's mind after looking at this particular like problem is like we can try out every particular subset to get the sum, right? We can try out every particular subset and then we can check if the sum is equal to like the target sum. So in order to try every particular subset, we basically iterate over each element, and for each element we have two options. Either we can include it in our subset or we cannot include it, right? So guys, this is how we are going to get every particular subset. If we have n elements, so for each element we have two possibilities, so the total number of ways will be 2 raised to the power n, isn't it, guys? And this is what the number of subset is in an array, right? So how we are going to do this, let me explain. Initially our I is equal to 0, right? And we need a one more variable, guys, which is sum. Why we need sum? Because we want to keep track of sum, so that whenever sum becomes equal to target, so we are going to stop at that point, right? So we have sum initially equal to 0 and this is our I, right? So now what we are going to do is initially we are at 0th element, which is 1, right? So we are simply going to have two options for this. Either we can include it or we cannot include. So this is the case for include and this is the case for don't include, right? After this, guys, see, if I include this particular element, so sum is going to increase. Now the sum will become equal to 1, right? Because we have 1 in the subset. After this, my I is also going to increase by 1. Why? Because I'm done with this particular element and now I'm pointing to this element, right? So I will simply write 1 in place of I here. And if I don't include 1, so I will have I equals to 1 because I is definitely going to increase, right? And after this, my sum will remain 0. Now see, guys, for this particular case, again we have two choices. We can either include the first element or don't include the first element. And first element is 5. So if I include 5, then sum will become 1 plus 5, which is 6. And I is also going to increase. I will become 2, right? After this, why I will become 2? Because I'm done with this particular element. So now I have to point to this element. But let me write the case for second, first index for every particular possibility. So see, here I will write 2 comma and I'm not including the current element, so it is going to remain same. Now what about this? So if I include 5, then I will simply write here 5, sum as 5, because sum is 0 and 0 plus 5 is 5. And if I don't include, then the sum is going to remain 0 and I will write 2 here. After this, I'm pointing to this particular element, right? So guys, what I'll do is I will again write one more possibility, and you can see that we have total 8 ways, right? We have total 8 ways. So the first way says that now I will become 3 in every case. So when I becomes 3, guys, before I becomes 3, I have choice, like I can include this particular 11, right? So 11 plus 6 is equal to 17. After this, I have one point here where my I will write 2, and if I don't include, then 6 is going to remain same, right? Sum is 6 here. After this, here if I include 11, so I will have sum equals to 12, and if I don't include, then sum is going to remain same, which is 1. Here if I include, then 11 plus 5 is equal to 16, right? And here if I don't include, then 3 comma 5. Here I'll write 3 comma 11 if I include, and 3 comma 0 if I don't include. Now I will come to the last element. So last element is This one, right? This one. This is index 3 and this is our last element. So for this element, again, I have two choice for every case, right? Two choice for every case. So let me write all the choice, guys. See, the first choice says that I'll increase I by 1 and 17 plus 5 is equal to 22, right? I will explain in detail how actually it works. After this, guys, I'll write 4 comma 17 because I'm not including the current element. Here I will simply write like 4 comma 6 plus 5 is equal to 11. Then I'll write here 4 comma, this is like 6 because I'm not including, right? After this I have 4 comma 12 plus 5 is equal to 17, and here I'll write 4 comma 12, which is simple, right? Here I'll write 4 comma 6, and here I'll write 4 comma 1. So this is how I can write every possible way, but I'm not writing every possible way because you can see that we have reached our target here, guys. This is what our target was. Now I have seen sum 11, so this means that I have found my subset. Let me explain what is the subset. Here I have included 1, right? After this, here I have included 5. Then this particular case, the right part is for not including, so I have not included 11. So it is like if I have 1 5 11 5, so include 1, include 5, don't include 11, and then again include 5, then again. So this is the set which is going to give us the sum 11. You can see that I have 1 comma 5 comma 5, and this is going to give us the sum 11, right? So guys, we have arrived to our subset. And let me explain some more possibilities. You can see that I have included 1, then I have included 5, then I have included 11 here, then I have included 5 here, right? So you can see that this is like including the whole array, and this is going to give me the sum 22 because the sum of whole array is 22, right? So this is how it works, guys. If I don't include any element, like don't include, don't include, don't include, don't include, so the sum is going to remain 0, right? So guys, this is what the approach is. Now from this we are going to figure out how we are going to write the approach, right? So see, I have the function here, I have the function here, and I have written the array as well. See, we have I every time, we have sum every time, and as this is a function, so this is going to take target, array, and n as well, right? Now guys, what I'll do is, see, if I include this particular element I, like which is 1, if I include 1 in my subset, then my sum will become equal to 1, right? And I will look for the remaining sum which is 10 in the remaining array, right? So I want to look for remaining sum in the remaining array. So how I can do this? This means that I want to find a sum equals to 10 in this particular array. So this is again the same function. This is again the same function, right? So what I can do is I can call the same function. I'll say that, okay, include basically means that I have check. This is like include basically means that I have check then I plus 1, because we were doing I plus 1 in every case. Like if I'm here, then I will do I plus 1 here and here, right? After this, guys, these are the two cases. So if I include, then my sum is going to increase by that particular value. So now my sum will become equal to sum plus array of I, right? After this, I have my target, array, and n as it is, right? So I'll write target, then array, then n. This is my first possibility. After this, what is the second possibility? It says that don't include. So don't include, in the don't include case, again I am going to write the same thing, but a little bit of change is there. I plus 1, then sum is going to remain same, sum will not change, right? After this, I have target, array, and n as it is. So target, array, and n, right? So you can see here, guys, I have target, like sum is going to remain same if sum is 0 here, and if I don't include, sum is going to remain same, then again sum is going to remain same, and even here as well you can see that if I have 1 and I am not including, so sum is going to remain same, right? So that's why I'm not changing sum. Now guys, these are the two possibilities, like right, like either this can give me the answer or this can give me the answer. So let's say if this gives me true and this gives me false, so I'm simply going to return the OR of these two. Why? Because I want the answer to be true in that particular case, because I'm able to find, right? So I'm simply going to return the OR of these two possibilities, right? Now this is a recursive function. You can easily find this particular thing, that I'm calling the same function again. So I should have a base case, right? I should have a base case, like when I'm going to stop. So I will simply stop, guys. I will simply stop at the point where my sum becomes equal to target, isn't it? So if my sum becomes equal to target, in that particular case I'm simply going to return true because I have arrived to my target. So I'll simply return true. After this, what about the second case? So the second case basically says that if my sum is not equal to target but my I has arrived value n, this means that I'm done with all particular element either including or not including, and there is no any element left, right? So in that particular case, I'll simply say that, okay, return false. I hope you understand these conditions, guys. But there is one more condition. There is one more condition. See, what if sum plus array of I becomes greater than target? Let's say sum plus array of I becomes target is 11 and sum plus array of I becomes 17. So what to do in that particular case, guys? There is no any case to handle it, right? So I'm simply going to first consider this particular condition. If my sum plus array of I becomes, guys, I'm simply writing pseudocode, so don't get confused like I'm writing sum here, then I'm writing sum here. Both mean same to me, right? Because I'm writing pseudocode. So if sum plus array of I is something which is greater than target, then like I cannot include the current element. So this condition will not be there, this first condition. So I'll simply do return check, return check I plus 1, then simply write sum because I cannot include in this particular case. Then target array and n is going to remain same. I have target, then array, then n. This is a very important condition to handle, guys. Now this is the whole approach that we have. This is the whole approach that we have. Once you have written this, your task is done, but you have to follow this particular thing as well. This is about check function. This is about the main idea behind the solution, right? So guys, once you have done this, your task is done. Talking about the time complexity, so see, this is basically going to try out every possibility, right? So for each a particular element, I have two ways, either include it or not include it. So 2 for first element, then 2 for second, then 2 for third, then 2 for 4. So it is 2 raised to the power 4. 4 is n here. So if I generalize this, then O of 2 raised to the power n is a time complexity, guys. And space complexity is also same because I have a recursive function, right? So guys, this is about the first approach. Can we optimize this? So of course we can optimize this, guys, and let me tell you what is the optimal approach we have. For that, we have to observe this particular recursive table that we have. See, let me change the color first. So guys, you can see that I'm solving 4 comma 17 here, right? And I have the same sub problem again. Then you can see that I have 4 comma 6, then I have 4 comma 6 here as well. So this is basically I'm solving the same problem again and again, right? I'm solving for 4 comma 17, then I'm again solving for 4 comma 17. But my question is, if I have already solved that particular subproblem, so why to solve this particular subproblem? So this is something which is the case for overlapping subproblems, right? Overlapping, let me write this, overlapping subproblems. And we can like already see one thing, that we have optimal substructure, guys, right? We have optimal substructure because every solution to any problem basically depends on solution to subproblems. This is what optimal substructure is. And if both these conditions are true, then the given problem is a dynamic programming based problem. And now guys, you can simply look for the topic tags for the problem. It is basically a DP problem, and I have explained the intuition behind this, right? So now we just need to do we just need to apply memoization technique. What we can do is we can basically store every sub problem, right? Like first I will store this particular sub problem, and then before solving this problem again, I will check if I have already solved it, right? So how I can do this, guys? I can simply have an array which is DP, right? I can have an array, and this is going to be a boolean type array. This is going to be a boolean type array, right? And initially this is going to store null. And see, before I solve any sub problem, I have to store it somewhere. So I'll say that, okay, let me simply write before, so if I return it, I'll write dp of I comma sum equals to check, right? And here also I will store it dp of I comma sum. I'm writing in I comma sum because I want to like represent every subproblem uniquely, and you can see that uniqueness of every subproblem basically depends on I and sum only. You can see that every particular value is unique here. Why it's unique? Because I'm changing either I, either sum, or both, right? So guys, this is what I'm doing. Now what is the size of this array? So this is equal to n comma total sum of the array, because these are the possible values for I and these are the possible values for sum. So now guys, I hope the idea is clear to you. I have stored every subproblem. Now before I solve any subproblem, I will simply check if my dp of I comma sum is not equal to null, right? If it's not equal to null, this basically means that the problem is solved. It is either storing true or false. So I'll simply say that return dp of I comma sum, right? So guys, this is what I need to do. Once you have done this, your task is done. Now your problem is going to have complexity of O of n cross sum. Why I am saying that? Because no any sub problem will be out of bound for this particular DP sub array, right? No sub problem is going to out of bound, because if the problem is out of bound, then it is going to give me an exception, right? But no problem will be out of bound for this particular sub array. And what is the size of this DP sub array? Like DP array. So the size of DP array is going to be n cross sum, because this is the size that we have, right? So guys, this is the time complexity, and space complexity is again going to remain same, n cross sum, right? Now I hope the idea is clear to you. I'm quickly going to show you the code, guys. So let me show you the implementation. uh, so this is the implementation in C++. Then we have Java implementation as well. Then we have Python implementation. Guys, Java implementation is bit tricky. See, we have to use a wrapper class, which is a boolean, right? You can see that I'm using capital B here, so that I can store null values as well, because only in wrapper class I can store null values in a boolean array. And if I write a simple boolean, then it is either going to store true or false. Now this is about the like we have a CPP code here, right? And you can see that here I am simply using a vector of integer, and this is going to give me the answer. Now this is the Python code, guys. This is the Python code. You can see that I am using a to-do list in place of DP here, which is initially storing none, because in Python we have none, right? And after this we are simply going to perform the same task. So now guys, this is about this video. Thank you.